Xu Xiaowei, and my student ID number is 111061203. In this video, I'm gonna show the derivation of electromagnetic wave equation by the differential form of Maxwell's equations. At the beginning, let's take a look at the electromagnetic wave equations. So this picture is the propagation of the wave, and then the gray one is the propagation of the electric field, while the purple one is the magnetic field. And then these two equations are the electromagnetic wave equations with respect to electric field and magnetic field. Then let's recall the Maxwell's equations that we learned from the physics class. We're gonna use the differential form of Maxwell's equations in free space. The first one is go slow, and the second one is go slow for magnetism, and the third one is Faraday's law of induction. The last one is Ampere's circuitous law. So let's start with the electromagnetic wave equations with respect to electric field. We're gonna use the third equation here. So for the first step, we take the curl of the both sides, and then we'll get del cross E equals to negative del cross partial B partial T. And here we can change the order of the partial derivative, so we'll get negative partial del cross B with respect to T. And then for this term, we're gonna use the vector identities here, this one. So we can rewrite it as this del cross E will equal to gradient of del dot E minus the Laplacian of E. And then from the first equation here, we know that this term is equal to 0. So we get del cross E equals to negative Laplacian of E. So we get the negative Laplacian of E equals to negative partial del cross B with respect to T. And then we can rewrite it as the fourth equation. It will equals to partial mu naught epsilon naught partial E partial T. And then we take out the constants. So we'll get negative mu naught epsilon naught. And the second partial derivative of E respect to T. And then we eliminate the negative sign of the both sides of the equation. Then we will finally get the Laplacian of E equals to mu naught times epsilon naught times the second partial derivative of E with respect to t. And this is the electromagnetic wave equation with respect to electric field. So we're done. And then the second one, we're gonna prove the magnetic field version. So let's take a look at the fourth equation. Similarly, we take the curl of the both sides as well. Then we'll get del cross B equals to del cross mu naught epsilon naught times partial E partial T. We take out the constants and also change the order of the partial derivative, and we'll get mu naught times epsilon naught times partial del cross E with respect to to T. And then we also rewrite del cross B as the gradient of del dot B minus the Laplacians of B. And from the second equation here, we know that this term is equal to 0. So del cross B will equals to negative Laplacians of B. And then we'll get the Laplacian, negative the Laplacian of B equals to mu naught epsilon naught partial del cross E with respect to T. And we will write it by the third equation. We'll get it equal to mu naught epsilon naught times partial negative partial B partial T. And then we take out the negative sign and combine the two partial derivative. We'll get it equal to negative mu naught epsilon naught the second partial derivative of B with respect to T. And then we eliminate the negative side as well. We will finally get the Laplacians of B equal to mu naught epsilon naught times the second partial derivative of B with respect to T. And this one is the electromagnetic wave equation with respect to magnetic field. So we have done, and this is all the content of my video. Thank you for watching.